Last time we started neutral geometry, and we had left off talking about exterior angles. So just as a reminder of where we were last time, we had talked about this kind of shaded and highlighted in red angle being an exterior angle. An exterior angle is supplementary to whatever angle we're referencing for our triangle. And then the other two angles that are not sort of marked in red here are called remote interior angles. All right, so we're going to continue on to the exterior angle theorem. And we'll abbreviate it EA when we need to use it in the future. And it's marked as 4.2 in your book if you were to go looking for that, okay? Exterior angle theorem 4.2. If any Hilbert plane, do you guys remember what a Hilbert plane is? Audience participation time. Anybody remember?
It's a model in neutral geometry.
Okay, so it's a model for neutral geometry. It's what we're referencing, right? And we had a couple of examples of that: the Cartesian model, and what was our other one? I don't have my notes from that. What was our other one? The Klein model, exactly. Okay, so we're working in a Hilbert plane, which is neutral geometry, so we do not have a parallel postulate. However, we did encounter last time that the elliptic parallel postulate doesn't hold in this particular geometry, right? Okay, so in any Hilbert plane, an exterior angle of a triangle is greater than either remote interior angle. Okay, so visually speaking, we all say, well, yeah, I mean, right? That angle right there is an obtuse angle, the one that's highlighted in red. It's the exterior angle. The other two angles are not obtuse, okay? The proof is in your book, so I'm not going to go through it with you. I will tell you where it is specifically. I know sometimes I don't always do that, but the proof is on pages 164 to 165. Oops. And it talks about that. Now, if you would imagine this case and how sort of maybe you could think about it, if you had one of the remote interior angles that was obtuse, how would that actually affect the exterior angle? And you can very quickly find that there's going to be a problem with sort of supposing that that's the reality, okay? So we're going to take a look at a couple of corollaries to that, or one corollary, excuse me, to that. So a corollary to this is if a triangle has a right or obtuse angle other two angles are acute. Now, inside of Euclidean geometry, which we have just left, basically, we could very quickly say we understand why this is the case. Why would this have to be true? What do you know about Euclidean geometry and triangles? specifically angle measures of triangles.
They add up to 180.
They add up to 180. Less than or equal to 180 is going to hold for our triangles here as well. Yeah. So they actually equaled 180 before. We haven't proven they have to be less than or equal to 180. Hopefully we'll get to that today. But it is a true fact for Euclidean geometry that they have to equal 180. Now, interestingly enough, that's equivalent to having the Euclidean parallel postulate, which is an interesting fact. So we don't have that in neutral geometry, but we will have the less than or equal to 180. Now, when we get to the fact that we've got the less than or equal to 180, this seems to be an obvious fact then, right? If I had an obtuse angle, or let's just use a right angle for that matter, 90 degrees, and if I have 90 degrees or less left over, then obviously the other two angles have to be less than or equal to 90 degrees. That wouldn't be possible, or less than 90 degrees if you've got two of them. Okay, so proposition. We're going to have a couple of propositions that you guys have seen before. They actually hold in neutral geometry, so that's kind of fun. So the first proposition is proposition 4.1, and it's the side angle angle proposition. And it says the following. Given AC congruent to DF, angle A congruent to angle D, and angle B congruent to angle E, then triangle ABC will be congruent to triangle DEF. And pictures are often helpful, so we'll draw one in real quick. So the pieces that we have with our argument right here, our statement here, is that side AC and DF are congruent. So those are our two sides. B is congruent to E. And, oh, I skipped one. A is congruent to D. Okay. Now we have had one triangle congruence before now. What was it? Yeah, it was side angle side, and it was an axiom. It was axiom C6, C5. I feel like it's C6, but one of our congruence axioms back in the earlier chapter. So this is a new fact, and you actually use that fact, right, from the axioms in order to prove this one. We're not going to do it in class on that one either. We're going to do some other proofs today, but that's how you do it. You do it with that particular axiom that we took to be true, and it didn't have proof for, right? Axioms we don't prove. Another similar one that you have seen is proposition 4.2, and it's called the Hypotenuse Leg Theorem. And that's abbreviated HL when you see it usually, hypotenuse leg. And it says the following: two right triangles are congruent if the hypotenuse and a leg of one are congruent respectively. To the hypotenuse and a leg of the other. Just for a picture's sake at the moment. Oops. We're going to mark them. So if I have the hypotenuse here, and I have either leg, I'll just mark the one on the right instead of the one on the bottom. Why would this have to be true? Why would those two triangles have to be congruent based on everything that we've done right up until this particular proposition?
Side angle side.
Close. Now, we have two sides in an angle on this one, right? That's different. The angle actually isn't trapped between the two sides. That's why it's not side angle side. But again, if we go back to side angle side, if we go back to side angle angle, we've got these relationships that we can use in much the same way. Unfortunately, we don't have a side-side angle postulate. And we talked about that before when we did constructions, that there's actually two ways you could draw that so that it would fail when you have particular ones, but it doesn't fail if you have a 90-degree angle. The reason it failed, if you'll remember, is that one could be acute and the other obtuse, and that's not possible if you've got a right angle. Okay? All right, we're going to shift gears just a little bit. We're going to talk about a couple other features of segments and angles. Proposition 4.3 specifically talks about midpoints. And this is an existence and uniqueness theorem, and it says the following. Every segment has a unique midpoint. And I'll write in what I actually just said a moment ago. It says that it exists. That's one of the things that this theorem says. So it's existence. And it's also talking about the fact that it is unique. And right along with that, right, we can cut segments in half, so to speak. That's something we're able to do, and we can do it in a unique way every single time, is Proposition 4.4, which equivalently says the same thing about angles. So Proposition 4.4 is about bisectors in particular. This one has two parts. The first one says, it is the equivalent of what we just did for 4.3. Every angle has a unique bisector. Right? If I can cut segments in half, so to speak, I can cut angles in half. That's what that's saying. And then on part B, I'll actually give you sort of a justification by picture in a moment on part A. But for part B of this one, it says that every segment, because we're back to segments now, has a unique perpendicular bisector. There's actually more going on in that second statement than you might have thought. For one, it sort of feels like it's a lot like the first statement. I mean, a segment would simply be like a 180-degree angle, right? So that makes sense. But with the 180-degree angle, I can certainly bisect it. If part A is true, part B would be true about the bisecting it. But it's got this additional fact about it being a perpendicular bisector. So you actually have to be able to show that you can get those 90-degree angles out of it, which isn't a huge stretch, obviously, because a line itself would have if you think about it as a linear angle, would be 180 degrees. But there's a component in there that you have to prove that's slightly different than part A. I'm going to give you sort of a proof by picture. So this isn't a real proof, okay? So we're going to start out with an angle. So draw yourself an angle. We'll label it ABC. And we're going to put the angle bisector, so to speak, in here. Or we're going to put what we assume to be an angle bisector, okay? And we're going to show that it would, in fact, have to be. So here's what I would assume to be my angle bisector. And I'm going to draw it. Obviously, there's infinitely many points on this particular gray ray, if you will, that I just created. And so there's going to be one that's going to be halfway, or not halfway, excuse me, but it's going to be between A and C. So let me draw that in. Okay, so we'll call this point C since I did it nicely. And I'm sorry, that was not drawn well at all. Let me try one more time. That's pretty believable. We know that A, B, and AC could, I'm sorry, A, B, and BC could be congruent. We just have to create it that way on our angle to choose the points A and C to make that happen. All right, so here's my point that I wanted. This was point D, I'll call it. So if you take a look at this, the whole idea was that we bisected the angle, right? That we cut it in half. And so there's a couple of ways that you could think about sort of arguing this. You could talk about the fact that if we know that these angles are congruent, if it's been cut in half, then clearly we have side angle side, right? And if we have side angle side, then that would have the concurrent triangles. This would be a unique bisector that is able to do that because we have these segments over here congruent. Okay. Another way to think about it, and the other one that I'm going to mention is more directly to the proof of this particular argument, is again, we can create these two particular line segments, AB and AC, and I keep saying AC, AB and BC so that they're congruent. That's not a problem. Obviously, BD is congruent to itself in the middle. And there is a value, namely from the, if we connect A and C, it's a segment. And according to what was it? No, it was on our same screen, wasn't it? Just the top, yeah, 4,3 on the top here. There's a midpoint, and D can be labeled as that midpoint. And if D is the midpoint, then we know that AD and DC are congruent, and we have what? Side, 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 which we did last time. I think we encountered side, side, side last time, I'm pretty sure. And so, excuse me, that's proposition, maybe it wasn't last time. Looks like it was further back. Proposition 322 is side, side, side. So with proposition 322, we actually have two, again, congruent triangles. The two congruent triangles would then make this for sure an angle bisector because those two angles would have to be congruent. Okay, so proof by picture for you today. All right, we're going to move on to proposition 4.5. Proposition 4.5 says in a triangle, ABC, this is a fun fact, the greater angle lies opposite the greater side. And we can say it backwards of that. The greater side lies opposite the greater angle. We actually had a theorem in chapter 3, an isosceles triangle theorem, and it said that when we had an isosceles triangle specifically, right, two sides that were congruent, that wasn't what I meant to draw, try that again, that we had congruent base angles, right? So we have these two sides, it automatically made these two angles congruent. Obviously a related fact. This one's talking specifically about what happens when they're greater than each other instead of having the relationship where they're equal. But this is a very similar kind of an argument. When I have equal sides, I have equal base angles. So if I have one side greater than another one, I will have one angle greater than another one. So let me actually draw this in a way that looks a little bit more, whoops, like all the sides are different. I don't know. Maybe that's pretty good. So in this argument, what side is my smallest side? Visually, it looks like AB. Remember, the way that we can do AB is you can either just write AB down, that would be the length of AB, or if you want to do the M in front of it to do the measure of it, that would be fine as well. Those are two different notations that mean the same thing. So the measure of AB is the smallest one. What does it visually look like? Just use your best judgment. Is the next longest side? I think it's BC. That's the way it looked like when I was drawing it as well. So this is less than or equal to the measurement of BC, specifically less than, in fact, but it would work if they were equal as well because we have the other isosceles triangle theorem that we talked about before, and that means AC is the biggest. So what this is saying is that there is a relationship between the angle measures then. So if I'm talking about side AB, I'm talking about angle C, correct? So the measure of angle C is actually less than or equal to the angle opposite the measure, the angle opposite the side BC. What side angle is opposite side BC? Yeah, it's angle A. So this is the measure of angle A. And then, of course, our last angle, the only one that's left, is angle B. Angle B is, in fact, opposite side AC. And this is what our theorem is telling us. Okay, our proposition is telling us, is that that relationship holds. And not only does it hold in that fashion, but if we had looked at the angles first and then looked back at the side lengths, we could have done the reverse statement. Combining a couple of these facts together is in proposition 4.6. So if we are given a triangle ABC and, whoops, I left the C off, and a triangle A prime, B prime, C prime, if AB is congruent to A prime, B prime, and BC is congruent to B prime, C prime, then if angle B is less than angle B prime, or angle, I shouldn't have said it that way. Let me move this if out of here. Angle B is less than angle B prime, if and only if, there's where my if is. If and only if AC the measure of angle AC is less than the measure, not angle, why did I say angle? Side. Measure of side A prime, C prime. There you go. And we actually used this fact, maybe it was hidden a little bit as you did it, when we were doing our basic constructions. We made a lot of arcs, didn't we? When we were trying to make angles doing certain things. You did it on your test too. You were trying to make an angle that was a 15-degree angle, trying to make an angle that was a 75-degree angle or 90-degree angle. We made a lot of arcs to do that. And when we made those arcs, our statement was basically that any point along that arc would have the same distance away from the center point that we were using, right? And that's essentially what's happening here as well. So if I have triangle ABC, okay, so right now, if you take a look at those two side lengths, they're the same. I copied and pasted them, so I know they're the same, okay? And then, if we can get this to cooperate with me, I don't know if it will or not. Yeah, it will. Well, if I don't, okay, I'm trying to not move my distance away. I'm just moving the angle measure, okay? So the side lengths are still the same unless I screwed it up by accident, okay? So this side length is congruent to this one, and this one is congruent to this one. And in doing so, if I were to finish the triangle, so to speak, out, what we see is that the smaller angle is opposite the smaller side, and this angle being bigger, I'll mark it double, is opposite a bigger side. And that's all this theorem says, okay? That if we fix the two sides to being congruent and we manipulate the angle and or the side, one or the other, then the other piece will also be manipulated likewise. All right, we're going to talk a little bit about measurements now of angles and segments because we've been talking a lot about angles and segments. This is measurement theorem 4.3, and it's talking about the angles first. There is a unique way of assigning a degree measure to each angle such that the following properties hold. All right, we're going to call this property 0. The measure of angle A, and there's another way that your book writes this. This isn't as common in literature, but just so that you're aware that you can do it. If you take the angle A and you put parentheses around it and put a degree marker after it, that's another way of writing that same fact. So if you like that, I'm cool with that. If you don't like it, just ignore it and use the other notation. This is a real number. Between 0 and 180. I'll be using the M angle notation. That's the one that I'm most comfortable with. So. In particular, what that's telling you is that if you're dealing with an angle, you need to measure this part and not this part. All right? You can pick which one you would measure. Like, you have a choice. So we're going to pick the smaller of the two. That's all it's saying. We can assign a number to be that. Fact 2 that we're calling 1. The measure of angle A is equal to 90 degrees if and only if angle A is what kind of angle? Equal to 90. Right. Yeah, a right angle. The next one. The measure of angle A equals the measure of angle B if and only if angle A is congruent to angle B. There's a relationship, right? Congruency means equal measure. We run into this, particularly my other geometry class that I have a lot, where we mix the notations together kind of at will. It's not good notationally speaking, but we understand that this relationship means the same thing.
Did you mean to write measure of angles?
Oh, yeah, I did. Oops, thank you very much. We'll fix that right away. There's a B there. Trying to fix something just a sec. Okay, number 3. If ray AC is interior to angle DAB, then, yeah, we'll leave it there like that. The measure of angle DAB is equal to the measure of angle DAC plus the measure of angle CAB. We had a similar statement about this with segments, and we called it the segment addition postulate. Does that ring a bell? You guys had a segment of subtraction one that you proved. This is the same thing for angles. So if I have an angle, DAB, and C is somewhere in between, so that there is another angle in here through C, then this angle, so the red angle plus the pink angle, well, we'll do even better. The red angle plus the blue angle equals the purple angle. You like how I did that? Yeah, some colors going on there for you. All right, it's angle addition. The angle addition postulate would be another way of describing that. And the last one, no, it's not the last one. I'm just got to turn my page. The next one for angles, number 4. And I'll use the next screen. There's not going to be enough space to finish it out, so we'll go up to here. Number 4 says for every real number x, between 0 and 80, I think I said 80 and I meant 180, between 0 and 180, there exists an angle A such that the measure of angle A equals x degrees. Now, does that mean that there are 180 angles? Is that what that's saying? No. What's wrong with me saying it that way?
So you'd be counting, x would be a natural number.
Right. It would be only using natural numbers to do that, or maybe whole numbers if we talked about a 0-degree angle, if they're 181 or something. All right, number 5. if angle B is supplementary to A, then the measure of angle A plus the measure of angle B equals what? Right, equals 180. Even if you run out of space at the end of your line. All right, the last one for angles. The measure of angle A greater than the measure of angle B happens if and only if angle A is greater than, sorry, I'm laughing because I have a typo in my notes, is greater than angle B. So the numbers have to work out right. That's what that says. Yeah. All right, so that was angles. Let's talk about some segment properties. Given segment OI, called a unit segment, there is a unique way of assigning a length measure of AB. So this is one way to write it. You can write it just AB with nothing on top of it. That means length. Let me write it that way. To each segment, AB, such that the following properties hold. So this is number 7 on our list, if we continue our list. The measure of AB is a positive real number. And that segment we talked about at the beginning, OI, is equal to 1. That's what we're meaning by unit segment, obviously. That's the number we assign to our unit segment. Number 8, the measure of AB equals the measure of CD if and only if what? They're congruent. I know, shocker, right? AB is congruent to CD. Number 9. B is between A and C if and only if the measure of AC equals the measure of AB plus the measure of BC. We've seen that once before. What do we call that? Segment addition, yeah, I hear a couple of people whispering it, yeah, that's a segment addition postulate. It doesn't work if they're not collinear, right? It has to be collinear to work. Right? That's what that first part means, the betweenness axiom there, or betweenness statement there. Number 10, just got 2 left. The measure of angle, I don't know why I keep saying angle, the measure of AB is less than the measure of CD. If and only if segment AB is somehow smaller than segment CD. Obviously very similar to the congruent statement. And our last one says the following. For every positive real number, X, there exists a segment AB such that the measure of AB equals X. Fun little history fact for you, because I happened to think of it as I was writing that one there. You guys are familiar with Pythagoras, right? Yeah, why are we familiar with him? Do you know? What do you know about him? The Pythagorean theorem, yeah, you know the Pythagorean theorem. I'm not trying to trick you, I promise. The Pythagorean theorem, and it talks about triangles, right? Which we've been talking some about triangles in here. And one of the things that he sort of gets credit for in the fact that his name's associated with it is Pythagorean theorem, although it was known long before Pythagoras. And the interesting fact is that he actually didn't like it, right? You have philosophy stuff going on here, right? He did not like it, and the reason he did not like it is because it proved the existence of irrational numbers, like square root of 2, something that you can't actually measure. You can actually get a radical that doesn't have a decimal expansion that stops, right, that terminates. And that's what's going on here in number 11 as well, right? You're saying that any real number, because that includes the irrational numbers, we have the ability to make a segment of that length. So, fun stuff.
They didn't believe in the irrational numbers.
No, irrational numbers was no good. So this was like a big secret, like hush hush, you know, like secret society kind of stuff. And yet he gets credit for, I don't know, kind of hiding it, I guess you could say. And the Mayans knew it long before Pythagoras too. So, all right, corollary number 2. So this is corollary. And just for instance, it's corollary 2 to the exterior angle theorem. All right, that's what it's for. It says the following: the sum of the degree measures of any 2 angles notice it said 2 angles, not 3. Any 2 angles of a triangle is less than 180. Now, in Euclidean geometry, this is sort of a silly thing to say, right? But in neutral geometry, this is kind of the best we can do. I am actually going to prove this one with you. You're probably wondering, are we going to prove anything today? Because I haven't done a lot of that except for a proof by picture. We are going to prove one today. This is the one we'll start with anyway. We'll see how much further we get. I'm going to draw a picture first so that we have a reference to be able to talk about the angles themselves. So here's the picture we're going to draw. I want you to do better than what I just did. Draw a segment AB, and we'll draw a triangle up from there, A, B, C, like this. And we're going to call this point A, this point B. We're going to do C as our third point of our triangle, and D is our ending point over here. Okay. All right. First fact. The measure of angle CBD, looks like a P, is greater than the measure of angle A. Anybody remember why? We'd actually talked about it today specifically. This one. Why is that one? Well, we did talk about it today. Yeah, it was the exterior angle theorem. You could abbreviate EA. I probably should have, and that would have saved some space. Oh well. Adding the measure of angle CBA to both sides gives the following. So we have the measure of angle CBD plus the measure of angle CBA, still greater than the measure of angle A plus the measure of angle CBA. All right, I'm going to add numbers together. There's nothing about that that's terribly tricky. This is all numerical, like these are, right? When I put the M's in front of them, we're talking about actual numbers. But what does the right side equal?
180.
It equals 180, because it's a linear pair or supplementary angles. So I'm talking about this angle in red and this angle right here in sort of black next to it. And whoops. This equals 180 degrees. I'm totally running out of space. Let me do it this way. Oh, hang on. I think I wrote it down wrong. I'm sorry, just a second. I'm trying to get my own angle measurements moved. The left-hand side is what I meant to say. I had it written on my notes right, but I said it wrong. Hang on a second. Let me move this. Here we go. This will make it easier. On the bottom, these two are my 180. I said angle A and I meant the left-hand side. Those two angles equal 180. So that 180 is greater than the measure of angle A plus the measure of angle CBA. Is that better, Kennedy? CBA is what we call angle B within the side of our triangle, if you prefer. So angle A and angle B were the two that we actually used. I'm marking them not to say that they're congruent, but those two particular angles add up to being less than the 180 degrees that we got from the angles right here added together. All right, moving on, we're going to talk about next the triangle inequality theorem. It says the following. If the measure of AB the measure of BC and the measure of AC are lengths of the sides of a triangle ABC. Then the measure of AC is less than the measure of AB plus the measure of BC. And there's absolutely nothing in this that's specified where A, B, and C have to be. So I could switch any of those letters around, doesn't really matter. All it's saying is that one side length has to be shorter than the sum of the other two. And this explains why you see signs that say keep off the grass. Why do people do that? Why did the people walk across the grass? Because it's shorter. Exactly. It's shorter than going on the sidewalks because they don't have the angle. And that's what's going on in this theorem right here, okay? So if we're thinking about this, we can prove it pretty easily when we keep that perspective in mind, okay? So we're going to prove this one. There is a unique point D such that B is between A and D and BD is congruent to BC. And this is our first congruence axiom, axiom C1. And it'll help us if we, since we started creating things, if we draw a picture that shows what we just created. So our picture is going to look similar to the one we just had on our previous problem. It's pretty good. Here's A, here's B, and here's D. And basically all we did when we were creating this is that we took the triangle ABC and we extended the ray AB beyond B far enough that this piece, did I get it right? I was about to say the wrong. No. That this piece, BD, is congruent to BC. There we go. We're actually going to connect C and D as well in a moment in our language, so I'll go ahead and connect it right now in our picture. Oh. There we go. All right, in this picture, there's an isosceles triangle. Do you see it? Yeah, absolutely. So, triangle. I think I'll skip the space. Triangle CBD is isosceles. And isosceles triangles, as I referenced and mentioned earlier, have congruent base angles. So angle BCD is congruent to angle BDC. Make sure I get it in the right. In red. Congruent base angles. And just as a reference again, that has a proposition. This is proposition 310. Okay, so when we start making claims, we should justify why we're allowed to make them. That's proposition 310. And then by theorem 4.3, part 9, that's that 11, well, it was really 12 parts because we started with 0. But by theorem 4.3, part 9, the measure of AD equals the measure of AB plus the measure of BD. Call it segment addition. But BD, the one that I just referenced, is the same as BC, right? Measure of BD equals the measure of BC by theorem 4.3, part 8. Substitution gives us the measure of AD equals the measure of AB plus the measure of BC. By proposition 3.7, that means that CB, the ray CB, is between CA and CD. Hence, angle ACD is greater than angle BCD. All right. It's on the outside of it, so to speak. Thus, angle, I'm not going to have space there. ACD is greater than angle ADC. And that's from proposition 3.21, part C. Finally, by proposition 4.5, side AD then is greater than side AC. And then the measure of AB plus the measure of BC would have to be greater than the measure of AC. You've heard analogous statements in sort of everyday conversation to things like the shortest distance between 2 points is a straight line, right? Or maybe you've heard the phrase, as the crow flies. It's all about this particular argument. All right, shifting gears just a little bit, we're going to talk about a couple of different kinds of quadrilaterals. I'm not sure if we'll get to the actual definitions of all of it today. The names of the two types of quadrilaterals that will finish out this section about neutral geometry, probably next class period, are called Saccari, S-A-C-C-H-E-R-I, and the next one is Lambert, like the home of the thrilled roll. Do you guys know what I'm talking about?
Yeah.
Anybody go to Branson? Yeah, I like that place. Okay, quadrilaterals. Okay, so we're going to sort of step back a little bit from triangles, though we're going to use triangles within here, and we're going to talk about quadrilaterals. So some definitions. So So this is a preliminary definition before we're actually going to get to those particular quadrilaterals. Quadrilateral and we makes it look like a square-ish shape. We're going to call it ABDC, in which the adjacent sides angle A and angle B are right angles will be called, you could say, or is called, by right. And by just means two, so that's why that's happening there. We will label such a quadrilateral so that the first two letters denote vertices at which the quadrilateral has the right angles. Side AB, joining the right angles, will be called the base. Its opposite side CD will be called the summit. Angle C and angle D will be called the summit angles. And CA and GB will be called the sides. And it's just begging for a picture, isn't it? It's a lot of language right there. As a general statement, what you're going to do is you're going to draw a rectangle, okay? We don't have all the rectangular properties per se, but the general shape is always drawn for this as a rectangle. they mentioned that the angles A and B are the ones where we are given that they are the 90-degree angles. Okay, so there's our two angles marked 90 degrees at the bottom. This bottom part is called the base. Each of these on the side are called the sides. So this is a side, this is a side. At the top, this is called the summit. And the angles at C and D are called summit angles. I'll give you one more definition and then we'll stop for today because it actually gives me one of the words that I called this section. This is the carry quadrilateral. This is a very important definition, so important that we're actually going to call it an important definition. Do you like that? Important definition. A bi-right quadrilateral and remember the notation, I put the little square looking shape A, B, C, D, so A and B are those right angles, in which AC is congruent to BD is called a secary quadrilateral. Okay, so picture-wise, it's almost like what I just drew. What one additional fact do I need to add? Doing everybody talk at once. You bet. The sides are going to actually be congruent. It's the only difference. Now, where we're headed next is talking about our next proposition that we'll start with next time. Actually talks about that those two sides being congruent is going to make the summit angles congruent. We already have base angles congruent, right? So they're going to be summit angles congruent. So this is kind of feels a little bit like an isosceles triangle at that point, where we're talking about it that way. But unfortunately, or I don't know about unfortunately, but we can't, inside of neutral geometry, prove that those top two angles, although they're congruent, are actually equal to 90 degrees on each of them, okay? And if we were able to do so, we would actually be attempting one of the arguments that has been proven along the way of the Euclidean parallel postulate not being a postulate, but actually being provable, okay? So we'll pick up here next time.